Welcome back. Again, my name is Dr. Wallen, and this is the second part in our Super Physics Tuesdays series of physics lectures where we're focusing on MRI physics. Again, here's the overview. Last time we went over some basic physical principles, the basics of magnetism, and a couple other topics like Fourier transform and stuff. Today I want to go through an introduction to gradients and really one step at a time go through how spatial localization is achieved. It's one of those things that I think confuses people a lot. Certainly when I was learning MR physics, I was constantly racking my brain trying to figure out, well, how do you know that this pixel is here or whatever? So we're going to go through this. Again, artifacts are spread throughout the talk when we're actually discussing the relevant physics that cause them. And at any time, if you have questions, just stop me, raise your hand, and we will try to address them straight away. All right, so one slide review of last time. Basically, you have to have odd proton number, odd mass number nuclei within the bore of the magnet, which applies a large external magnetic field. We've mentioned just offhandedly that we use gradients for spatial localization. You deliver an RF pulse, which rotates the overall magnetization from the longitudinal plane, the Z plane, into the XY plane. Then you listen through that same coil, and you listen to a signal which looks like a sync function as you get the information back. You convert, we had talked about this last time, you convert that echo or signal into a digital signal, and then you put that digital signal into a thing called K-space, which is an intermediate imaging space. Remember last time we talked about real and imaging spaces. You perform the Fourier transform, and voila, you get your image, which is a representation of real space based on a limited set of parameters that you're querying via some technology, in this case, NMR active protons within the bore of the magnet. Okay, so you can't listen to everything all at once because it would just be one lump of stuff. But you recall when we do receive the signal is a sum of all of the oscillating magnetic moments or protons that are NMR active that are within the bore. We have to do it basically one dimension at a time. And we can separate those out by manipulating gradients along the spatial directions. There's going to be one gradient per dimension, so obviously it's done in 3 steps, and space has 3 dimensions. The z-axis, which we also call the slice select axis, the y-axis, which we'll call the phase encode. Now you can switch these around, but for the purposes of our talk, y will be phase encode, also up and down, or A to P if a position is in the magnet. And the x-axis is the frequency encode axis, or frequency direction is left to right. Okay, so we're going to go through each one. We're going to go through them out of order. We're going to do Z first, then X, then Y. Trust me, it's just easier to understand if we go a little out of order. Okay. When we look at overall MR sequences, they're schematized in what we call a pulse diagram. So here's a pulse diagram for a spin echo image. This is the most basic an MR sequence can get. And we have a bunch of different components here, but I'll just walk you through it really quickly. This is the RF pulse, basically the transmit-receive coil line. So your RF pulse is going out as a transmitter line. That's a 180-degree pulse, which remember refocuses in the spin echo. And then that's the echo being listened to in the same coil along this one line, okay? So that's the standing electromagnetic wave inside the bore. Then the other 3 lines are in each of the 3 cardinal directions and represent linear magnetization in the form of gradients. So here along the z-axis, we have, we're changing up this gradient a couple times. Here along the y-axis, this is a phase encode gradient, so it doesn't stump you. The reason there's a bunch, this looks like a step ladder, is because when you take an MR image, you repeat this phase diagram multiple times. And at each one, the value of this gradient changes, whereas the value of this gradient stays the same, RF pulses stay the same, and our final gradient in the x direction, our read gradient or frequency gradient, stays the same. That was a crash course. I didn't explain anything, so that's what this entire day is going to be about. We're going to go through each one of these individually and very slowly, possibly to your chagrin. So let's start in the z direction, which is the slice select direction. All right. So step one, you apply MZ. Here's the bore of the magnet. We're looking from the side. Remember, Z is in and out of the bore. So when the gradient is off, let's see what it looks like. 1.5 Tesla magnet. The magnetic field is going to be 1.5 Tesla at the feet, going to be 1.5 Tesla at the head. There's no change. We're assuming that it's uniform. That's great. If you remember by the Larmor equation, which I said you had to know last week, 64 megahertz is going to be the base speed at which water protons precess in a 1.5 Tesla magnetic field. Okay, so everything's spinning at 64 megahertz. Great. Now turn on the Z gradient, see what happens. So now the gradient is on. That means that B0, the effective B0 along the bore of the axis is different and in a predictable way. So here I've just made it so that it's visually easy to see. B0 is about 1.4 at the feet, 1.6 at the head. Plug those into the Larmor equation. Remember gamma, the gyromagnetic ratio, does not change. Then you'll come to see that the protons in the feet are oscillating or precessing at 60 megahertz and in the head at about 68 megahertz. Okay, so just remember that. So this is how gradient basically works. It's setting these apart by changing the frequency at which they precess. Now, remember, when we send out the RF pulse to develop signal by taking away longitudinal magnetization and putting magnetization that's phase coherent into the transverse plane, we can only do that with an RF pulse if the RF pulse is sent out at a frequency that's equal to the precession of those protons. It's from last week, so I'm asking you to remember that. Now, if we were to generate here, in this example, a 90-degree RF pulse where the pulse is oscillating at 64 megahertz, then what's going to happen? Well, you're going to get some place in the middle here, a narrow range of protons that's going to be affected by the RF pulse. So you're going to generate transverse magnetization, but only where the protons are spinning at are precessing at 64 megahertz. That is to say, to belabor the point, the protons in the feet do not get excited, the protons in the head do not get excited, only at the frequency you send the RF pulse out at. Now, how do we make an actual slice or an axial image? Well, we have to set the thickness, and the thickness depends on both the transmitter bandwidth, which we'll talk about in a second, and gradient strength. So what is exactly the transmitter bandwidth? Well, the transmitter bandwidth is a range of oscillation. Here, let's just say we select it to be 200 kilohertz, right? So if we send out an RF pulse with a 200 kilohertz bandwidth around a 64 megahertz carrying frequency, I'm saying a lot of words, I know. Basically, that means we're sending RF waves in a continuous range from 63.9 to 64.1 megahertz. Okay, so that means that only protons that are precessing in that range of frequencies are going to be affected by the RF pulse. Well, now you see, if there's a range, well, that's why we have a slice thickness, right? So it's whatever that band of frequencies is that's set up by the gradient that get excited, okay? Now, the gradient strength is the other thing we can manipulate. Measure that in, say, Tesla per meter. Say our strength is 0.2 Tesla per meter. Well, that means, like we said, B0 goes from 1.4 to 1.6. But notice that if you were to change the slope of this gradient, then it would actually change the range of frequencies along it, right? So if at 1.4, protons are oscillating at, say, 60, and at 1.6, it's 68. Well, if you were to make this an even stronger gradient that went from 1.2 to 1.8, they'd be oscillating at, from 54 to 76 or whatever. So you can, if you do that, then the same bandwidth is going to only excite a narrower band, so it narrows your slice. Again, that was all in words. Let's just take a look at it visually. So in order to decrease slice thickness, if our baseline is a strength of 0.2 Tesla per meter and our bandwidth is 200 kilohertz, when you increase the gradient strength, notice the higher slope, that 200 kilohertz covers less dimension along the z-axis, thus giving you a thinner slice. You could also decrease the transmitter bandwidth. That is to say, the range of frequencies that your RF pulse is going out at, you can narrow that frequency range. And if you do that, even with the same gradient strength, you're also going to end up with a narrower slice, right? Of course, in either case, you're exciting less overall number of protons, so your signal is going to be lower. Keep that in mind. That'll be important later. Okay, so I'm going to ask you to recall when we talked about Fourier transform last time. Remember that when we're listening to these echoes, they're like these sinc functions. And sinc functions are composed of multiple fundamental frequencies. Okay, that's exactly what we're doing with the RF pulse, right? The RF pulse is about the same shape as the echo we get back. That's why it's called an echo, because they're kind of the same. So our transmitter bandwidth is going to be this rectangular range of frequencies, which if you Fourier transform that, would be a sinc pulse, right? So this is what our echo looks like. This is what our RF pulse looks like. And it's no coincidence that the Fourier transform of that is this rectangular function, which is a band of frequencies, hence the term bandwidth. How wide is this? Okay? So this is what it looks like. We generate a range of frequencies for the RF pulse to go out at. They all sum together in real space, and you have this complex oscillating RF field, which, if you record, looks like a sinc pulse. Okay. Now, how good is your slice? So that's how we're sending out a slice selective pulse and generating selectively exciting protons only within one slice. Now, how good is your slice, quote unquote? Well, let's look at the slice select profile. So that's something we talk about, basically the shape of your slice. Now, this is a nice slice, right? Say 8 millimeters thick, perfectly rectangular, great. And then this would be a bad slice, right? It's got angles on either side, and it's just not going to be exactly what we're thinking of when we think of a slice. So as an extension of Murphy's Law, basically anything in physics, when you think about it for us, for radiology, if there's two ways it can go, one is to make your life harder and one is to make your life easier, it's always going to go the way that makes your life harder. So this is what happens in reality. We basically always have quote-unquote bad slice, or at least non-ideal slice-like profiles. And why does this happen? It's because of the Fourier transform, right? Now let's take a little closer look. What would be a perfect slice selection? A perfect slice selection would be a perfectly rectangular slice. But in order to do that, your standing RF wave would have to be a perfect sinc function, which means it has infinite tails. And in order to achieve that, you'd have to send out an RF pulse with an infinite range of frequencies. Well, obviously you can't do that because it would take an infinite amount of time. And so instead what we do is we send out a truncated sinc function. Okay? Now, how do you send out a truncated sinc function? Well, pretty easy. We actually just, instead of using an infinite range of frequencies, we use a specified band of frequencies, i.e. bandwidth, finite bandwidth. And in real life, instead of having this perfect square wave of a slice, we have this red line, which is, there's sloping sides, there's side lobes, the top's uneven. Okay? Let's take a look in Excel where we can kind of control things a little more. I've generated a couple of data sets of sinc functions that are truncated at different levels. Okay, if we do the Fourier transforms of these three sinc functions, you'll actually see this effect come to life. So as at the top, there's a little bit more angle to the sides of the quote-unquote slice select profile, and the top is very much so flatter on the sinc function with the longer tails. Okay, so think about this. When we're sending out an RF pulse, the more time we invest in sending out that RF pulse, basically the better shaped our pulse is and the better shaped our slice will be as a result. Okay? So I guess you think, why is this problematic? Well, this is another artifact. Since we're talking about it, we'll talk about it now. Crosstalk artifact is the artifact that occurs in the slice select direction. And if we look at our real world quote-unquote bad profile, slice profile, we have in the green, the central portion, that 5 millimeter slice is the desired excitation, and then the red portion is the undesired excitation. Well, this has two effects, actually, so there are two parts to the crosstalk artifact. One is that we listen to everything at once. So when you image this quote-unquote green slice, you're also getting the information from the red on either side. So that means that information from tissue above and below what you're actually looking at is going to bleed into your image. Okay. The other problem is if you were to, say, image this slice and then the next slice, well, since you've inadvertently excited the protons in the red portion of this poorly selected slice, you're going to lose that longitudinal magnetization and you're going to have less signal when you try to image it in the subsequent image acquisition. Okay, so again, gain confounding signal in your desired slice, you lose potential signal in an adjacent slice. Okay, well, that's great. So we already talked about this. Now, how do you fix it? Well, basically, you can put more, go out farther on your sync function. So use a wider bandwidth. If you could increase the bandwidth, basically, you would, since you have a better shape, the loss of signal is going to be less from the next slice, and you're going to have less information bleeding into your slice. There's actually a better way to handle, so the information bleeding, really it's just how good is your slice. But in order to avoid loss in a subsequent slice, there's actually better ways to do it, which is either use an interslice gap. Here you see there's this tiny gap where we just skip over the red part and go to the next image. Or you interleave slices. So you image here, and then you image somewhere completely different, and just come back there later. So more TR times have passed, and your longitudinal signal is recovered. Okay, so now remember, changing the transmitter bandwidth and your slice thickness are actually exactly the same thing. They're completely linked through the Fourier transform. One is in real space and one is in frequency space. It's the same thing. Those two concepts are not separable. Remember that. Okay. So we talked about this. Okay, now also, as a third thing, besides the information bleeding and information loss in subsequent slices, there's also dephasing. Remember, anytime you have a gradient on, you're going to cause dephasing across that gradient because, by definition, it's making them spin at different rates. That means if you were to, when you apply the Z gradient as you're doing the RF pulse, you're necessarily causing dephasing in the Z direction, right? And so if you were to then image after that, you're going to have a lot of signal loss. So, kind of like when we do the 180 RF pulse and things passively rephase, and you get a reformed echo, you actually do something that's more direct, which is we apply the Z gradient in the opposite direction. So apply a negative gradient, which will unwind the dephasing that has occurred. Does that make sense? So I have to have the Z gradient on while I apply the RF pulse. That's how I'm selectively exciting only one slice. That's what it is that makes it those 5 millimeters of the image you're looking at. But I will have dephased all the spins from front to back in the Z direction. So I have this unwinding gradient, and that rewinds them, and now they're back into phase coherence. Of course, then free induction decay starts, et cetera, et cetera. Okay. So yeah, so always have to use a balanced gradient with positive and negative lobes. Remember, it's kind of like our animal waste. All right. Okay, question number 1. Oh, I didn't tell you guys to log in. Sorry. You can log on to your smart implements now. www.pollev.com/Walled, W-A-L-L-E-D. Up there. I'll just read the question while people are logging in. All right, so when a gradient, GZ, is applied for slice selection, there's a negative or rephasing lobe, which I just got done explaining. When we apply the GZ gradient during the 180-degree refocusing pulse, there is no rephasing lobe. Take your attention there. Right? You have to unwind that one. How come we don't unwind this one, basically, is what the question's asking. Is it because of crosstalk artifact? Is it because dephasing no longer matters at this point? Is it because the rephasing lobe is applied before the read gradient? Or is it because there is no net dephasing with the 180-degree pulse? Is it showing up on your devices? That's not the correct answer. Sorry, Larry. Oh, it sounded like a good song. Okay, so 6 people answered. Let's take a look and see what people said. Okay, so most people said there is no net dephasing with a 180-degree pulse. And, of course, yes, that is exactly correct. Since the nature of a 180-degree refocusing pulse is that it reverses the spins in real time, it takes them all the way from 0 to 90 to 180 in the xy plane. That means that the dephasing in the z direction that's happening as they go from 0 to 90 actually gets undone from 90 to 180. So there's no net dephasing, so you don't require an unwinding or negative load for that gradient. Okay. In this MRI sequence diagram, in what direction is the slice select gradient being applied? X, Y, Z, or not enough information? That diagram. And this is just practicing looking at pulse sequence diagrams. Okay, good. Most people said X, and of course X is the correct answer. When you look up here, you can see that where the slice select gradient has to be applied while the RF pulse is being applied. So no other gradient is on during this time except for the X gradient in this picture. That means this is the slice select gradient. Okay, and it's also applied, of course, during the 180 pulse because you have to selectively excite whatever's in your slice. Okay, good. Any questions? All right, how does one minimize crosstalk artifact in an MR experiment with the following pulse diagram? Do you use a stronger GZ? Do you introduce a slice gap of 2 millimeters? Do you use a stronger GX? Or do you increase the receiver bandwidth? Okay, most people said introduce a slice gap of 2 millimeters. A decent number of people said increase receiver bandwidth. Well, it's introduce the slice gap. So remember, there are 2 strategies, introducing a slice gap and increasing the transmitter bandwidth, right? So that's a trick. So the transmitter bandwidth and the receiver bandwidth are 2 different things. We'll talk about receiver bandwidth later when we talk about frequency encoding. But for the purposes of slice selection, it's all about transmitter bandwidth. And anytime you hear someone say bandwidth, or like a tech say bandwidth, or you're at the scanner and someone wants you to increase the bandwidth, they're talking about receiver bandwidth. No one ever talks about transmitter bandwidth because it's inherently linked to slice thickness. And no one likes to think about these things. Any question? Okay. All right, so assume, this is the long one. Assume GX is a linear gradient and our machine default yields a 5 millimeter slice thickness. A service rep comes and upgrades the GX gradient from 1 to 2 millitesla. So now that gradient is twice as strong. What is our new default slice thickness on this sequence? And how might we theoretically adjust the transmitter bandwidth to return the slice thickness to 5 millimeters? Is it the same and no changes needed? Is it now 10? Or is it now 2.5? And to fix it, do you have or double the transmitter bandwidth? So what happens if you double the gradient strength? And how do you fix it? Oh, good. Yes. Basically, everyone got it. Okay, so if you double the gradient strength, remember you're going to have a steeper gradient, so you're going to have you're exciting less protons in your selected bandwidth. So the new slice thickness is going to be 2.5 millimeters. And the way to then make it back to 5 would be to double the number of frequencies that you're including. Good. Okay, enough about Z gradients. Do we need a break? What do you guys think? No? It's only been half an hour. All right, good. So we'll move on from Z to the X and Y directions. Okay, now after we've selectively excited one slice along the Z direction, we're going to depict it now like this. So these are going to be our slices in the slice that we get in the axial slice. All right, so the phase encoding steps are going to be in the Y direction. Each single step in the phase encoding direction is going to represent the origin of one line of K-space. And then the X direction is going to be the read direction, or the frequency encoding direction. And this encodes the lines of K-space, each of which, of course, being initiated by a different and unique phase encoding step. All right, so we're going to discuss the frequency encoding gradient first, and we'll talk about this why later. All right, so how does it work? Again, the RF pulse generates the transverse magnetization. We have a phase encode step. This is basically just in words going through the pulse diagram. You turn on the phase encode gradient, wait for a period of time to turn it off, and then it'll offset all the different phases as a function of position in the Y direction. Then you go to your frequency encoding step. You turn on the gradient in the X direction, or the frequency encoded gradient, and you listen to the signal while that gradient is on. Okay. Once you turn that gradient off and stop listening, that completes the, quote, MR experiment. That's what they're called in discrete units. Okay, so just again to help you learn how to look at a pulse sequence diagram, each pulse sequence diagram represents one MR experiment, right? So in each, after slice select an RF pulse, you're going to have a unique phase encoding step, which in subsequent TRs is going to be different. And then after that, you can have a 180-degree pulse or not, whatever, depending on the sequence. When you listen to the echo, you turn on the read gradient, and you collect the echo while the gradient is on. Okay. Again, that spatially encodes in the read direction. So let's look at this. Now, assuming there is transverse magnetization in the XY plane, i.e. we've done an RF pulse, you turn on GX, right? So now instead of being a flat line, GX is varying from left to right. Well, you decide how many steps you want to break your x-axis down into, and this is going to give you the width of your image pixel. So the field of view, your total field of view, divided by the number of steps, which you set, which is called your matrix size in the x direction, or MSX. And this is going to result in columns of protons that are precessing at different frequencies, right? Larmor equation, lower B0 here, higher B0 there. Well, net B here and higher net B there. And as a result, these protons are going to be precessing at 61, say, through 66 megahertz. As you listen to them, you'll get a sync function, and you can use the Fourier transform to parse out the different fundamental frequencies from each column. Let's take a look. So remember, again, sync function, multiple fundamental frequencies. Now, these component frequencies, say the blue, the red, the green, and the blue, in order of increasing frequency, are going to represent different columns in space. So say that red represents the leftmost column of space, the green somewhere in the middle, and the blue all the way in the patient's right. Well, patient's left are right in the image. Excuse me. Now, each one of these fundamental frequencies is going to have its own magnitude or weight, which is determinable by the Fourier transform, and that magnitude is the amount of signal coming from that column of protons. The amount of signal coming from that column of protons is determined by the number of oscillating protons in that column. So you're starting to see how we're like able, okay, we can figure out which protons are in which column and how many there are in each column. Okay, so if you take that sync function and you do the Fourier transform, you'll get a histogram, right? Kind of like I was showing you last time, but now we actually are getting values. So when you make this histogram, the height of each bar in the histogram represents a frequency or a column in space. And the height of that bar represents the magnitude of signal, or how many protons are precessing at that frequency. Okay. Now, I want you to pay attention here, because I'm just going through I'm like talking about Fourier transforming individual results or individual echoes just because it helps us to understand that spatial localization is working. That's not what we do in real life. What we do in real life is we just convert that echo into a digital function, and we enter those digital data along a line of K-space. No Fourier transform yet. At the end of K-space acquisition, we do a 2D Fourier transform on the whole thing. So that is a difference, but I'm going to keep doing this like this just to show you how it works. All right. Now, this range of frequencies that vary around the central carrier frequency of a proton rotating in the native B0 of that magnetic field is that's going to be the receiver bandwidth. Okay, so here the gradient Gx is strong enough to make protons precess at plus or minus 3 megahertz from the central frequency, which is 64 megahertz. And we listen, and then here, in this case, right, the receiver bandwidth is 6 megahertz. Does that make sense? Right, okay, good. So, and that's what people talk about when they're at the console, and they're like, what do you want the bandwidth to be, whatever. Now notice 6 megahertz is a very large value. I did that only for the purposes of making the images neat. In the real world, we use much, much smaller. Okay. Chemical shift artifact. So this is a big one. They like to talk about this on the test and ask you a lot of questions about it. So this is a frequency encoding artifact. And I'm going to ask you, this is the huddle up symbol, because I'm going to go through a long bunch of steps, one after the other, and it'll pull together in the end. Now, remember, fat protons precess slightly differently than water protons in a 1.5 Tesla field. Specifically, it's 220 hertz different. Okay. Now, since the precessional frequency varies linearly in the direction of the read gradient, depending on the gradient strength, that's determined by the receiver bandwidth. Now, we've also broken up the x-axis into discrete step sizes, depending on our matrix size and how big we want those bins to be. As a result, we can define an artificial value, which we'll call the pixel bandwidth, which is just the overall bandwidth divided by the number of pixels. So how much bandwidth are we covering per pixel? Basically, how wide are those columns of protons in terms of range of frequencies? Okay. Now, if the difference between the precessional frequency of fat and water, call it delta omega, delta W for easy sake, and delta W, that difference in precessional frequency is wider than the bandwidth covered by a single pixel, then there's going to be misregistration of fat protons. Okay. Now, that is all in words. It's a lot easier to see it. So let's do some visual stuff. Thought experiment. Say we got some fat, some Crisco, sitting in a petri dish of water. Now, if we take a cross section like an MR image, let's say it's in a 1.5 Tesla magnet, then we're going to have, if we look at relative to the baseline water proton, the shift in frequency, right? Water should all be at 0, and all the fats are at negative 220. Now, if we turn on the gradient in the x direction, or the read encoding gradient, which say we have a receiver bandwidth of 1.4 kilohertz, then what we would expect if it were just a petri dish of water is this variation from negative 700 to positive 700 in terms of precessional frequency. Everyone follow me? Good. Now, in our experiment with the Crisco in the middle, what happens? Well, because these protons in the fat precess both as a result of the Gx gradient and because of fat's inherent difference in gyromagnetic ratio, causing it to oscillate at 220 hertz less, you're actually going to have negative 320 and negative 120, which look an awful lot like the pixels, one to the left of them. So let's just say, what does it look like? If we have pure water and we turn on the gradient and we image it, we get solid gray all the way across. Now, with our experimental dish, we see that actually these protons, since they're being read at negative 320, are registered to this third pixel. These ones are registered to this pixel, and now nothing is being registered in that pixel, which is what causes the distinct appearance of the chemical shift artifact. Okay? And here, I unfortunately did not do this experiment because it's very cool. Somebody actually put a blob of fat in a petri dish of water and put it in a magnet and took this image, and it's exactly what you see is white on one side, black on the other. And it's along the direction of the frequency encoding gradient, or the x direction, the frequency direction. Any questions? Good. Okay, so how do we fix it? Well, all you have to do, basically, is increase the gradient strength in the x direction, which is the same thing as increasing the receiver bandwidth. Why is that? Well, let's take a look. If now, instead of 1.4 kilohertz, we make it 11.2 kilohertz, so basically 10 times stronger than we've made the gradient, well, our experimental dish is going to look differently because, remember, the difference between fat and water, they're still sitting in a 1.5 Tesla field, so it's still only going to be negative 220. But now the pixel-to-pixel variation in bandwidth is much higher. So actually, the loss of 220 hertz is going to be felt much less. So you barely have any shifting quantitatively. Actually, it turns out to be about 12% of the shift instead of 100% pixel shift. So you might see a subtle change here, but the point is, the more you increase the strength of the gradient in the x direction, the more you increase your receiver bandwidth, necessarily because they're linked, and the more you're going to decrease the chemical shift artifact. Guaranteed you're going to have a question on your test about that. Everyone loves this artifact. Okay. I'm going to bite my tongue and tell you that there are two, those of you who've heard me lecture before know I hate the term chemical shift artifact for type 2, but we're going to say, because this is how they ask the questions on the test, that there are two kinds of chemical shift artifacts. So type 1, or chemical shift of the first kind, quote unquote, is exactly what we just talked about. Basically, you only see that above 1 Tesla, so in magnets, higher fields it's worse, and it's a signal misregistration across space, and you fix it by increasing the receiver bandwidth. Okay, now type 2, or chemical shift of the second kind, if you ask me, isn't really a chemical shift artifact, but some people call it this. You only see it in gradient echo imaging, and it's actually more of a temporal thing than a spatial thing. So you've heard of it more appropriately as the India ink artifact or signal loss on in and out of phase imaging. Okay, and this is proton signal cancellation due to time. The way you fix it is by only imaging at in-phase times. What do I mean by that? Well, remember we said fat precesses 220 hertz slower than water. So if we think about that, something that's going 220 hertz relative to something else, so let's be in the rotational frame of water protons, right? If something's moving 220 hertz relative to our not moving water, that means there's going to be a period of 4.4 milliseconds. So that means every 2.2 milliseconds, it's going to go from out of phase back to in phase, out of phase, in phase, right? And whenever you have both fat and water within the same voxel, if they're out of phase, their magnitudes are going to cancel. So you're going to get massive signal drop. Because when we do image, this is talk for later, but we only image absolute values of magnitude, right? So if there's a discrepancy, then that's why it looks black, because it's getting closer to 0 because the signals are canceling each other. So at any fat-water interface, there's necessarily a place where the voxel spans the two spaces, one of which contains fat, one of which contains water. That's going to look really black. If you have a small amount of intracellular fat, say in a fatty liver, then you're only going to get a small amount of signal cancellation because the number of fat protons is going to be opposing the water protons. So when you're out of phase, your overall signal is going to decrease. That's just a whirlwind tour of in and out of phase imaging, but some people call it chemical shift at the second time. Anyway, all right, let's do a couple questions. If your field of view is 50 centimeters and you've designated a square matrix that's 100 by 100 for your image, what is the width of a pixel in the x direction? Good, 5 millimeters. It's simple math, right? So basically it's just your field of view divided by the number of steps that you've broken it up into, or your matrix size in the x direction. Now remember I told you I was going to tell you when I was lying to you. I said it's the same thing as the in-plane spatial resolution. There's actually a much more complicated story to what in-plane spatial resolution actually is, so just be aware of that. But for superficial purposes, you can think of it that way, and it's fair game to ask you a question where that is actually the answer. Okay, so if the strength of your gradient in the x direction is such that water protons precess from 63.75 to 64.25 megahertz across the desired field of view, what is the receiver bandwidth that would give you the most usable signal? So 63.75 to 64.25 megahertz is the range of frequencies along the x direction that your protons are precessing at. as a result of the gradient, frequency encode gradient you chose. What receiver bandwidth will give you maximum signal? Let's see what he said. Good. Wow, everyone's getting everything right. That's very good. So 500 kilohertz, inseparable. Again, in real life, this isn't a designation you can make. When you say what the receiver bandwidth is, that's what causes those precessional frequencies. There is no mismatching in real life. Just be aware of that. But in theory, if you could somehow listen to a different range of frequencies, you would just be losing a lot of information. Okay. What is this artifact? And how do you fix it? Phase wrap or chemical shift? And do you increase or decrease receiver bandwidth? Yes, in fact, it is chemical shift, and you increase receiver bandwidth. Very good, in order to get rid of it. Increasing receiver bandwidth will increase the amount of bandwidth you have per pixel, which will decrease the relative misregistration caused by fat protons precessing at 220 hertz, less than 1. Okay. What must be true of the in these images of the central circle and the outer square being imaged? Is it that they're composed of different materials? Is it that the circle must be fat, the square is water? One contains paramagnetic material and the other does not? Or is it both A and B? They're different material, the circle's fat, the square is water. Ooh, 50-50. Composed of different material or both A and B. So that's good. That implies that everyone knew that this one was true. It's just 50% of you thought this one was also true. Well, it's actually A. It doesn't have to be fat and water. It could actually be any two things with discrepant gyromagnetic ratios. Remember, the Larmor equation doesn't just respond to fat and water. It responds to everything differently. So it could be any two substances that have different precession in the same magnetic field. Also, even if it was, say, fat and water, there'd be no way to tell which one is fat and which one is water unless you knew the direction of the frequency gradient, which is not specified here. So a bit of a logic thing too. Okay. Now, after a single MR experiment, so one of those diagrams, the receiver coil reads out echo number 1. After the depicted process, which is called ADC here, what does the height of one of these vertical red bars represent? So, kind of across the board here. Okay, the most answer was number of protons in the voxel. That's incorrect. It's actually the value of a point in k-space. So that's okay. So that's good. We've identified something that's not clear. So let's go over it a little bit more in depth. At the end of a single MR experiment, you have your frequency encoding gradient, and you read out an echo. Okay, that echo is in the shape of a sinc function, right? Now, your frequency matrix, how many columns you chose to split space into, is how many points that you're going to turn that echo into when you digitize it. This is an analog signal, right? Computers can't handle just looking at a waveform like your brain can. So it has to be digitized serially, okay? So the number of red bars is going to be equal to your frequency encoding matrix size, okay? Then these digitized values, -1, -5, 5, blah, 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 are going to be plotted along a single line of k-space, okay? So the heights of these bars are going to be the numerical value in k-space. Let's say this is your first echo. Then along the 0th line of k-space, you're going to have these numbers. End of experiment. You do another MR experiment with a different phase encoding gradient. Same frequency encoding gradient, now you have a slightly different echo. You digitize that echo, then you enter these heights as the individual numbers into the second line of k-space. Okay? So that's why the height is the value of a point in k-space. Strength of GX has nothing to do with it. You guys knew that. The number of protons within a voxel, that's never going to directly be the case, right? Because each point in k-space actually is relevant to every single pixel on the image, which we'll learn about later. And a precessional frequency, that's also incorrect. If you were to Fourier transform this, you would get a histogram. Each bar would represent a different frequency, and the height of those bars would represent the number of protons, right? So, and that's I want to make sure that point's clear, because we're kind of not talking about reality when we talk about doing 1D Fourier transforms on echoes, because that doesn't happen in real life. Okay. Which MR artifact is depicted by the arrows in the image at right? Is it chemical shift type 1, chemical shift type 2, intracellular fat deposition, or a flow void? What you guys said? Bada boom, very nice, 100%, yes. So this is chemical shift type 2. This is the India ink artifact. It's seen on out-of-phase gradient images. Chemical shift type 1, of course, is the point that I belabored about fat and water in a petri dish. Intracellular fat deposition is when you're going to have, say, the liver is bright on in phase and then gray on out of phase. And a flow void happens within a vessel. We haven't talked about that. That's a completely different mechanism. Okay. How could you get rid of this annoying black line in this 1.5 Tesla MR image, or in this image obtained in a 1.5 Tesla magnet? Could you decrease the receiver bandwidth? Could you switch the phase direction? Would you repeat the image with your TE higher by 2.2 milliseconds? Or would you use chemical fat saturation? Very good. Yes. Okay. So, no. Definitely. You'll put it back. Yeah. So it's repeating the image 2.2 milliseconds. Remember, this is a temporal thing. So every 2.2 milliseconds, the fat and water protons are going out of phase, in phase, out of phase, in phase. So if this is an out of phase image in 2.2 milliseconds, if you collect your echo, which is the definition of TE, then you'll have an in phase image, and you won't have India ink or any of the other chemical shift of the second kind artifacts. All right, so phase encoding. This is the last one we're going to talk about. You guys want to take a break? It's been about an hour.
A short break.
Yeah, we'll take like a 5-minute break about that. All right. Now, we talked about slice selection and frequency encoding and the GZ and GX gradients. So now let's talk about the phase encode gradient, which is this one, and it'll oftentimes look like this funky stepladder thing. All right. Remember that the frequency encoding gave you multiple columns in space of protons that are precessing at different frequencies. But the problem is there's no localization in the y direction. Okay, so how do we get localization in the y direction? Well, this is going to be multiple steps again, so try and stick with me. Decide how many steps you want. Let's say again this time that you want 6 steps in the y direction, right? This is going to be just like the other direction was your matrix size in the x direction. This will be your matrix size in the y or the phase direction. And it's also going to give you your pixel height, which is the field of view in the phase direction divided by the number of steps. And now you have 6 unknowns in each column, right? How many protons are in this one, this one, this one, this one, for each of the 6 columns. So if you remember back to algebra, you need 6 distinct equations to solve for those 6 unknowns, which means that we're going to need to repeat the MR experiment 6 times. So we're going to have to do 6 repetitions of the pulse sequence diagram with slightly different phase encoding gradients. That way we get 6 slightly different echoes. That then will contain the information that we need. Sorry, this is acting up. So that will give us 6 different sync functions, and the analog to digital conversion will give us basically a 6 by 6 case-based matrix. This is 36 unique coefficients over 6 variables, which if you ever took linear algebra, you would know allows you to solve it. Now, remember, Fourier transform is not about solving linear matrices, so that's why this is there. If you really understand this stuff and you're a senior that's following along with me, this will sound a little weird and off, and it's because it is. But I'm just kind of trying to prove to you that it works, and it can be done almost in this algebraic way, just so you trust that it works when we talk about the real way, which is, K-space. Hooray, have trust. Do the Fourier transform and believe it. Okay, so again, you're going to repeat the MR experiment 6 times with 6 different phase encoding gradients, right? Now, the higher you make your gradient in the y direction, the more dephasing you're going to have. So notice, so here's, say, GY1. Usually it's 0, but for the purposes of illustration, I made it a weak gradient. Notice that if you turn this on and turn it off, along the y direction, they're still going to be all rotating at 64 megahertz. But during that time that was on, right, the ones that were rotating or precessing faster gained phase on the ones that were lower down. So after it's been on and turned off, you've gained a phase offset, say 5, 10, 15, 20 degrees. And then you do higher and higher, you do more steps with higher phase encoding gradients, and notice that will cause greater phase discrepancies once they're off between the different rows along the y direction. Now, I'm just going to say this, we'll justify it later, but we always want your highest signal-to-noise ratio in the center of K-space. So we're going to collect our center of K-space, preferably with lower phase encoding steps, because we'll get more signal that way. And just trust that for now, and we'll talk about it later. All right, let's keep moving and actually try and look and get an idea for what's happening. So again, the image is broken up into different rows with different phases by the phase encoding gradient. So here we've selected 7 instead of 6 different rows. Again, that's your matrix size in the y direction. Now, you turn on the phase encoding gradient, you wait a certain time, and then you turn it off. I put this on repeat, they're kind of skipping around. But the important thing to notice is that as you go up, the arrows are pointing, are rotating or precessing faster than the ones in the bottom. Well, you leave it on for a certain time and then you turn it off. Remember, these are all in the relative place. So these are all rotating at 64 megahertz at baseline. So now they're all back to rotating 64 megahertz, but GY was strong enough and on long enough that we complete a cycle of 360 degrees from the bottom to the top of the image, right? That means that, so there's 0 to 180 above the x-axis, and 0 to negative 180 above the x-axis, and 0 to 180 below the x-axis, okay? Those are phase offsets. Now let's look, oops, sorry, boy. Now, again, we need as many phase encoded gradient steps as we did, we need as many phase encoding steps as we do there are lines of K-space, which is the same as the matrix size in the y direction, which is kind of the number of vertical pixels in the image. This, again, is a partial lie because you can have rectangular matrices and all sorts of stuff that mess that up. But just for now, we'll say that. In real-life scanning, the first phase encoding step is going to be 0 degrees. So there's actually going to be no phase difference. You just have like a mock phase on for a set amount of time. They all stay in phase, and there's no signal loss. Then again, you gain more. You have more steps with increasing gradients in the y direction. And the last step in real life, it's actually going to be many cycles over the vertical span of the image. So in this case, it goes from over a 360 cycle. In a real image, it'd be like 360 every line, basically, is going to be your strongest phase encoding step. Here's an example of a 3-dimensional K-space, real MR experiments. This is not my image. I took it off of Google like 4 years ago, so sorry I don't have a reference. But notice that in the x direction it looks like a sinc function, and then as you go in either y direction it drops off precipitously. Okay. Now, phase encoding, here's your artifact for the phase encoding direction. It's phase wrap, aka wrap or wraparound artifact. This is another question they love to ask on your test. Remember, You are going to define what the field of view is. Let's say 40 centimeters, okay? Now, in the frequency domain, your field of view is actually, it's not 40 centimeters. Linear measurements don't have meaning. Everything's cyclic and oscillatory. So instead, field of view is 0 to 360 degrees. That's all the frequency space can understand. Since sinusoids are cyclic and infinite, basically adjacent cycles are going to be equivalent to each other. 90 is the same as 450 is the same as 810. Whereas if you were looking at a linear graph, you could say, well, that one's there, and that one's there. You know, they're all functionally equivalent in frequency space. So if you have a signal outside of your designated field of view, it will still be measured because you can't help it. The antenna listens to everything in the bore of the magnet, no matter what, under all circumstances. It's all an additive signal, right? So it will be measured, but just at a position which is going to be an equivalent position outside of the 360-degree range, right? So to talk about it in math terms sounds really confusing. Let's just take a look. Let's just say this is something in real space, these three colored balls. The object is going to be 60 centimeters from top to bottom, but you, foolhardily, set your field of view to 30 centimeters, okay? Now that means that the machine's going to scale its 360-degree field of view over 30 centimeters in real space. So basically from negative 180 to positive 180. This is what, you know, you basically told it there's only stuff from there to there, okay? So what's going to happen? Well, it's still going to hear everything. So it's going to have to say, well, this stuff is in there, and has to assign it to somewhere. So the bottom wraps in from the top, and the top wraps in from the bottom. And that's what phase wrap is, and what it looks like. So how do you fix it? Well, there's a couple ways. One, you can increase the field of view, obviously, and then you won't have that problem as long as the machine's encoding it appropriately. Or you can use phase oversampling. In GE, it's called no phase wrap. So what is phase oversampling? Well, in our case, our field of view was 30 centimeters, but the actual object was 60 centimeters. Now, if we did 100% phase oversampling, what that's going to do is it's going to take an additional 100% of our field of view, so an additional 30 centimeters, and make the way it acquires over 60 centimeters. But it's going to actually throw out the oversampled part. So it's going to throw out the top 15 and the bottom 15 and just present you with the central 30. Okay? So these two techniques yield different results. When you increase the field of view, you actually get more signal, right? Because you're now looking at more protons than you were trying to look at before, but you're going to have less resolution because your field of view is bigger. In phase oversampling, it increases the amount of time that it takes to acquire the image because there has necessarily more phase encoding steps. There is no signal benefit, but you do have higher resolution, right? Because you're only looking at a smaller field of view. So we can kind of intuit that if we look at these pictures. So here's your phase oversampling. Look, it just looks truncated. It's because the machine imaged everything. It just threw out the top and threw out the bottom. And then there's if you were to increase your field of view to 60. Now, again, you can imagine if these were images of a brain or something, you can kind of intuit that this would be higher resolution than this. You'd be able to see more detail on that. You'd have more signal to noise in this one, just because there's more protons, but you wouldn't be able to see as small of features. So here's, in real life, what it would look like. Is a sagittal image of a brain with wraparound artifact. The nose is wrapping in through the back, and the back of the head is wrapping in through the front. And if we were to flip that and look at an axial, you can see what it looks like there. And this is also an excellent image, not mine, but from a very old Google search. As you decrease the field of view, right, you start to introduce this phase wrap. But notice what happens to the in-plane spatial resolution. Here you probably can't read at this point. It's basically 1 millimeter, and here it's 0.5 millimeter. So you can tell by looking at the picture, you've got more detail in there, but you also have the wrap. Okay. Any questions on that? All right, let's do some questions. If you want to have an image with a square 128 by 128 matrix, and you're doing a basic spin echo sequence without acceleration, how many phase encode steps will you need? Excellent, 128. Everyone got that one correct, right? So you have to repeat the MR experiment 128 times. You get one echo per phase encoding step in a regular spin echo sequence. Okay. This one's a little tough in terms of its length, and you got to think about it. All right. Let's just say we're doing the third MR experiment. So you're on the third phase encoding gradient, and it looks like this. It's of this strength, and it's left on for 3 milliseconds. This gradient induces phase shifts from -90 to +90 from the bottom to the top of the image along the y-axis. For the next phase encode gradient, GY4, how long does it have to be left on to make the protons now at the top and the bottom of the field of view to be 100% out of phase from each other? Is it 6 milliseconds, 9 milliseconds, 12 milliseconds, or is it still 3 milliseconds, but you have to use half the gradient strength? It's a tough one. I'll give you guys a few seconds to figure it out. All right, most people said, okay, so we got 6. A couple said 9, and some said 3, but half the gradient strength. Well, it's 6. Okay, so there are two options. Gradients are always linear, and they're basically the integral of their strength, which is their height, and the length of time that they're on for. So you can, the initial one is from -90 to +90, right? Now, if you want them to be 100% out of phase from the center, that means they have to go from -180 to +180. And that means that you're getting twice the amount of phase shift. So the gradient you need is going to cause twice of the phase shift that the G3 gradient caused. Now, there are two ways to do that. You can leave it on for the same time and double the strength, so twice the strength for 3 milliseconds, or same strength with 6 milliseconds. Okay, so the answer is 6 milliseconds. Because it was 3, then you could double the gradient strength. Make sense? Gradients are always linear and cumulative. All right. Now, you image this patient's upper abdomen with a field of view of 40 centimeters using a standard 2D spin echo sequence. The result is seen below at right. What are the encoding directions of the scan? Slice, phase, and frequency. Match those up with left to right, A to P, anterior posterior, and S to I, superior to inferior. 2/3 of you said this one, let's see, and then a couple people said each of those. So the majority is correct, but let's look at the two that people got it wrong. So it's an axial slice, right, which means that necessarily the slice select gradient was applied along the z-axis. So slice is superior to inferior. That's the slice direction. So it's got to be one of these two, so that's why it's not this one. Now, here we're seeing wrap. Remember, wrap artifact only occurs in the phase direction. Wrap does not occur in the frequency direction. So that means that necessarily left to right is the phase direction. So S to I, left to right, this is the correct answer. And by default, frequency is A to B. Any questions? Okay. Now, similar case, you image this patient's upper abdomen with a field of view of 40 centimeters using standard 2D spin echo sequence. When you get this result, what process labeled with question marks is used to fix this image? So the first time you get this image, then you did something else called question mark, and you got this image. What is the question mark? Is it phase oversampling, increased field of view, decreased field of view, or phase undersampling? You guys responded pretty quick to that one. And yes, most of you got it correct. Phase oversampling. How do you know it's phase oversampling? Because it's getting truncated. So if the image looks like it's cut off, right, this can't happen in the phase direction truly. So you had to have acquired the data and just thrown it out, which is what phase oversampling is. If it had been increased field of view, then you would see the entire abdomen and it would be lower resolution looking. Phase undersampling does not exist, and decreasing field of view would have only worsened your problem. Okay. After imaging a brain with a field of view of 20 centimeters, you notice a significant wrap artifact. Of course, since you're smart and you come to my lectures, you double the field of view to 40 centimeters so there is no longer wrap artifact. Now, assuming your in-plane nominal spatial resolution had been 1.5 millimeters, sorry, Paul everywhere doesn't allow you to use periods in your questions, what will your resolution become after changing the field of view to 40 centimeters? Okay, so field of view of 20 centimeters, your in-plane resolution is 1.5. When you double the field of view to 40, what is your new resolution? Let's see what people said. Ooh, 50-50 tie between doubling and halving. Well, I'm glad that happened because this is kind of confusing. Now, it's 3, and let's go through this slowly, right? So if you're doubling your field of view, so there's a couple ways to approach this. If you double your field of view, your resolution is going to get worse. So you know your resolution should be worse. Forget the factor or whatever. When you give a single number a dimension for an in-plane spatial resolution, that's basically kind of, that's why our friend is there, kind of saying that's how small of an individual thing you can pick out. So with a field of view of 20 centimeters and X technique, you can pick out a 1.5 millimeter thing, right? If you double the field of view to 40 centimeters but have the same matrix size, so the same pixel values, each one of those pixels is going to be fatter, coarser, less spatial resolution. So you're going to only be able to see something that's about 3 millimeters. So when they give you an individual number like this, higher numbers is worse. An in-plane spatial resolution of 3 millimeters is twice as bad as 1.5. Okay. Notice when we talk about X-rays and stuff like that, we talk about spatial resolution in terms of line pairs per millimeter, then a higher number is better, because they're actually saying how many things per millimeter, right? It's an inverse ratio. Any questions? Okay. All right. We're going to try and depict a fake MR acquisition. Now, instead of using K-space, I'm going to do something we don't actually do in reality just to prove to you that it works. So this is a real big caveat. This is not real. This is not how MRI works. It's just to prove to you that spatial localization can be achieved with gradients. Okay. Again, normally when we get an echo, we digitize it, add it to K-space, and then we do a 2D Fourier transform of all K-space. But this example is inspired by Vivian Lee, who's one of my personal MR heroes. This book, Cardiovascular MRI, Physical Principles to Practical Protocols, is actually how I learned MR physics. And it's just a great single resource. And despite the title, it's actually not just about cardiac MRI. You'll learn basically all of MRI in the process. So highly recommend it. Anyway, all right, let's start our quote-unquote simulation. So first step, as we know, is always slice selection. So we got the slice select gradient GZ turned on, RF pulse. That knocks magnetization from longitudinal into the XY plane. Here's our, right, this is our, what did radiologists do? Real space. Here's a real space object, which is just say a gradient, right, from this corner to that corner of proton densities. Okay, so it's water in different concentrations somehow, magically, against gravity. Shouldn't need it. Whatever. Anyway, all right, we're going to image this. In order to keep it simple so that we can actually do the math, we're going to use a 3x2 matrix, okay? Again, we slice selected. While that was on, we did an RF pulse, which generated MXY. So this is our slice. This is MXY, okay? We have the Y direction here and the X direction. We've chosen 3 for our frequency encoding direction is our matrix size in the X direction, and 2 is our frequency size in the Y direction. And here are gradient indicators. GY and GX are both off right now. Each of these white circles represents the population of protons within the real space that we've broken up into this 3x2 matrix. The red arrow is the direction, or the overall phase at t is 0 when everything is phase coherent. Okay? And then the number is the frequency at which they're spinning. Of course, I've kept them still so that you can see them. All right. Everyone with me on our basis here? Good. So, first thing we do after we've slice selected and developed MXY is we do a phase encoding gradient. Okay. So apply the first gradient. GY is on, GY is off. Nothing happened, right? Well, great. That's expected because remember I said oftentimes our first phase encoding step is going to be gradient of 0. So we applied a 0 gradient to this and nothing happened. All these protons are just spinning at 64 megahertz. Okay, great. So there's no phase offset in our real space anymore, but we're going to move on to our frequency encoding and readout. Okay. Now, say we turn on this 1 millitesla gradient. GX is on, look what happens. Now, from left to right, there's a difference in the speed at which these protons are precessing. 63 at left, 65 at right. Notice GX is staying on, okay? So while GX remains on, we're going to listen to the receiver coil, and we're going to get this sync-like function. I hope I've said enough sync enough times that you guys are no longer intimidated by the fact that it's a function you never heard of. Okay, here, this is the complete disconnect from reality, what we do not do in real life, but we're going to do, for our purposes here today, we're going to Fourier transform this individual sync function, okay? And then we're going to plot the magnitudes as a histogram versus fundamental frequency, okay? This is our result. Now we're going to write these numbers down that on the left side of the image, we got a magnitude value of 63, of 75, 124, and 184. Okay? Done. MR experiment number 1 completed. How many do we need? 2, because there's 2 phase encoding steps. We set our phase encoding, the phase direction of our frequency matrix to 2. Okay, so for the second one, well, we do the same RF pulse, a slice selected RF pulse, and then it's time for the second phase encoding step. So we waited, of course, we waited TR, so there's some MZ recovery, forgot to mention that. Slice select, RF pulse, boom. Here we have our transverse magnetization. Now, we're going to apply our second and final strong gradient in the Y direction, call it 1 millitesla. Watch what happens. So GY1 is on. Now, there's a difference, right, in terms of their X position for a little while, but then we turn GY off. We set GY to be strong enough and on long enough that from this row to this row, these spins are now 180 degrees out of phase. Makes sense? Okay, now, a little more boring, we're going to apply the same frequency encoding gradient that we applied the last time. So when we do that, notice GX is on. Same thing happens. Now from left to right, there's a gradient or a difference in their precessional frequencies. Notice, however, though, that they're out of phase with each other. So they're precessing at the same rates vertically, but they're 180 degrees out of phase with each other. Okay. We listen while GX is still on, of course, as we always do, and we get this sync function. Notice how much smaller the sync function is. That's because these are now out of phase. So the bottom row and the top row signal contributions are canceling one another. So we get this more diminutive sync function. Okay. Now, again, complete disconnect from reality. We Fourier transform one-dimensionally this echo, and we get another histogram representing the relative contributions of the fundamental frequencies, which represent the different columns in space of these precessing protons. Record your values, 9, 34, and 15. Okay. So, to take, a bird's eye view, we had experiment number 1 for these 3 columns that are in phase going at these different frequencies. Then, experiment 2, we had these 3 values for these 3 columns which are out of phase, and we recorded the numbers. Okay. So, again, we broke up the space into a 3x2 matrix. So the first experiment is going to give us our first quote-unquote case baseline. Again, please notice this is not real case space. This has already been Fourier transformed, so it's ruined. It's not a real case baseline, but I'm just calling it that. We enter the values. Okay, and of course GY was 0. Now what does GY 0 mean? That means if these spins are in phase with these spins, and here and here and here and here, then these total values are the sum of the 2 contributing individual cells, right? That would lead us to 3 equations. A1 plus A2 is 75. B1 plus B2 is 124, C1 plus C2 is 184. Okay. Now, similarly, we're looking at the second line of pseudo K-space, which is already Fourier transformed, and we get these numbers. Well, these were 180 degrees out of phase, right? That means that the values of relative abundances of protons within the column are the result of a subtraction. So that gives us these equations. A1 minus A2 is 9. B1 minus B2, because they're out of phase, is 34. Same for C. Right? Now, look at this. We have all these different equations. Again, just reminding you, it's not real, not real K-space. But we have all these equations. And if we look at K-space, so say a black background is 0 signal. This is the pseudo K-space. And increasing tan is more signal. When we plot these in, we can kind of see that it does not look like the real space, right? It's because it's an abstract version. Somehow we're extracting information, but not by representing the real space yet. Again, probably too many disclaimers. I know you guys get it. But all we do is solve the equations, which will be like our pseudo Fourier transform. All right. Remember, we had the pluses and the minuses for being in phase and out of phase. And now you can just do simple substitution for each variable. Right? If A1 plus A2, say A1 equals A2 plus 9, that means 2A2 plus 9 equals 75, so 2A2 equals 66, but whatever. So we can just do this. And then, so A2 is 33, you plug that back in, you can get all these numbers, algebraically solve it. Now this artificial algebraic Fourier transform is the real space representation. When we actually put these numbers as grayscale or tan scale values back into our individual matrix squares, we get a real space representation. It's a gradient from the upper left to the lower right-hand corner of proton density. So one more time, bird's eye overview. We have a real space image that is a varying amount of proton densities. We do the MRI, which gives us a real-world version of Fourier transforming into K-space of one form or another. And then the K-space, when you mathematically Fourier transform that, here algebraically, you then get an image, and that's it. And so these spatial encodings work, and you can prove it in this reduced special case. Even algebraically, you can prove it works. So with a more complicated mathematical technique like Fourier transform, it stands completely to reason, right, that it works. I'm just trying to make you guys trust it, because I know no one believes in K-space. They think it's all gibberish and fake. All right. So enough with that. Let's ask some overall, likely testy kind of questions. Which of the following represents the correct sequence of events when acquiring a spin echo MR image after the application of a slice select gradient in RF pulse? So you already did the slice select gradient in the RF pulse. What? Good. DBCA is the correct answer. 2/3 of you got that right. A couple people said switch the B and the D. Let's see. So frequency encode, phase encode. Right. So you always have to do the phase encode first, because when you actually get the echo is when you're frequency encoded. So you phase encode, turn it on, turn it off, create the phase offset. Then you listen while frequency encoding. That gives you an echo. You analog to digitally convert that echo. And then you enter those values into K-space. You Fourier transform K-space. That's your image. That's the sequence of events. Okay, match the artifact with the appropriate directionality. We got wrap, chemical shift, crosstalk, and RF leak, and then slice direction, frequency encode direction, node direction, or phase encode direction. Ooh. Yeah, maybe. Okay, yeah. So 50% of you said, I think, the right thing. Everyone knew that A, wrap, was the phase encode direction. B, chemical shift, is always in the frequency direction, so it's a B2 that knocks out this one. And then crosstalk that's in the slice direction, so it should be C1. And then RF leak, we didn't talk about it, but RF leak is if you have the door open or something and a cell phone signal comes in, you get a frequency spike from the RF, actually energy coming from electronic devices outside the Faraday cage of the room. So yes, nice little overview on artifacts and directions. Now, match the artifact with the relevant imaging parameter that fixes the artifact. What the hell? Oh, there we go. 50-50. Okay, well, let's go through these. So wrap, how do you fix wrap? Wrap is a phase encoding error. Two ways to fix wrap: either increase the phase field of view, or do phase oversampling. Phase oversampling is not an option, so it's A4. Right, so it's one of the two. Chemical shift, that's a pixel misregistration due to different gyromagnetic ratios and a phase shift, so or frequency shift. So if you increase the gradient in the x direction, or the read gradient, which is the same thing as the receiver bandwidth, then that's 2, so it's B2, so it's this one. And then crosstalk artifact, well, that's in the slice direction, so that's the transmitter. Good job. Right, so if you increase the transmitter bandwidth, you'll have more frequencies included, a better shaped sync pulse for your RF pulse, and thus a better slice-like profile, and less crosstalk artifact. Okay, good. All right. When an echo is digitized, ADC, or analog to digital conversion, how many discrete points does it get converted into? Is it the number of phase encode steps per image? Is it the number of frequency encodings per image? Is it the matrix size in the phase direction? Or is it the matrix size in the frequency direction? Ooh, okay, so we're kind of all over the place on this one. The correct answer is matrix size in the frequency direction. Okay, so I think, and this is probably one of the most confusing parts. At the end of the MR experiment, we have on the frequency encoding gradient, and we collect an echo, right? And that's this analog standing waveform inside of the bore of the magnet that we're listening to with an antenna. Okay, we have to turn that echo into something a computer can handle. That's the analog to digital conversion process. Now, in order to do that, you have to pick how many bins you want to specify across the width of the echo, right? And that's determined, how rapidly you can sample this is determined by your frequency encoding gradient strength, or your frequency. So this is a frequency encoding thing, you can think about it as. So it's actually the number of your matrix size in the frequency encode direction, okay? Now, the matrix size in the phase direction, that's going to determine how many different MR experiments you have to do, assuming you get one echo per TR. And so the matrix size in the phase direction is more like, how many MR experiments do I have to do? Or how many lines in K-space are there? Okay. Number of frequency encodings per image, that's kind of awkwardly phrased. That's not even a real thing. I presume that there is a certain case where if it's a square matrix, that is true, because then it's equal. And then the number of phase encode steps per image is the same as the matrix size in the phase direction. Any have questions about this? This is a pretty tough concept. Okay. All right, and that's it. So next we'll be talking about signal to noise ratio and imaging quality.